There we go. Thank you. Okay. Well, now someone's going to watch the video, wonder why the person got so much bigger. But in summary, when you are a little bit under the surface of the water, there may be a little bit of pressure on you, but the further down we go, the more we tend to notice that pressure in our ears and maybe even other parts of our body, okay? And so where that pressure comes from is the sort of column of water that is above us. Like here, there's more water above us, and so it's going to cause more pressure, whereas here, there's only a little bit of water above us, so it's going to cause less pressure, okay? Is the recording sign on right now?
Yes.
Okay, cool. All right, so what's new? We're going to take this sort of phenomena of fluid of force, okay, increasing as we go down below the surface. And we're going to think about it now in terms of not people, but objects, okay? So let's say that you have some fluid. It might be water, it might be oil, it might be a lot of things, but some sort of fluid. And underneath this, you are taking some plate and we are submerging it in the water. Okay, so we're taking this plate, we're sticking it in the water, but sort of vertically. So, okay. So this is the plate submerged in water. All right. Now the area of the plate, we're just going to call the area as A. All right. There is the density of the fluid that we'll need to consider. So that'll be rho, our friend rho. And then the amount of force on this plate is also going to depend on the depth. And we'll call that little d, okay? Now, kind of like our last example for 6.5, where we had the bucket of coal at the bottom of the mine shaft. And like the lower the bucket was, the more work it took to move that bucket, because at the lower end, there was more cable, which meant there was more weight or force. And so kind of similarly, like there's more pressure at the bottom of the plate than at the top of the plate. And so we can't just say like, this is the force for everything. We need some sort of function to model this, okay? And so what we're going to do is do this. So we're going to walk through an example, and we're going to learn how to draw a diagram, and then we're going to figure out how to come up with the equation. So this is going to feel a lot like that tank of water where we were pumping water out of the tank. We're going to kind of, again, approach this with like, what are the different parts of the formula, and then at the end we'll have a formula that we can generalize for all the other examples, okay? So for this one, all right, it says find the hydrostatic force against one side of a triangular plate. So let's kind of sketch sort of the surface of the water. And then this plate actually has dimensions, okay, a certain dimension. So it's a right triangle. And it kind of looks like this. And you'll see in the other problems that we're going to do, the description of the plate is going to be much more exact. So we'll tell you the dimensions in there. But for this case, I really wanted us to focus on sort of this bigger process, okay? So let's say that this plate has a base of 5 meters. And let's say that this triangle also has a height of 4 meters. Okay, so 5 meters by 4 meters. And it happens to be the top of the plate is 3 meters under the water. Okay. So again, at the top of this plate, so if I'm looking like here versus here, the green part has more pressure than the purple part because it's down below the surface of the water further than the purple part, okay? And so what we're going to do here is we're going to imagine we're taking just one slice out of this triangle. And our slices are going to be parallel to the surface of the fluid. So let's pick our slice to be somewhere like maybe here, okay? And even the thickness of that line is too thick for the slice that I'm actually imagining, okay? But we're using it to just kind of think about one particular piece. So this slice, I want us to imagine it as a very thin rectangle. Right, it is a very thin rectangle that goes parallel to the surface of the fluid. So it is parallel to the surface of the fluid. Okay, so if we imagine this little rectangle, right? If I'm thinking about like X and Y, this thickness of the rectangle, is that represented by X or Y?
X.
Why is it represented by X?
Get back Y.
Why is it represented by Y?
Because it's the thickness of it, not the distance of it.
Yeah, and maybe more simply, it's just sort of in our traditional Y direction, right? Y is sort of vertical, X is horizontal. So when we're looking at that thickness, the way that our picture is oriented, that is a Y distance. Now, we want this to be really, really thin, okay? So if it becomes really, really thin, then we're thinking, okay, like when we have integrals, the reason we have like the dx's and the dy's at the end, that dx or dy represents sort of the thickness of any given slice that we're taking. So that distance right there, we could say is dy. Now, the horizontal distance, we're going to call that the width of the rectangle. All right, the width of the rectangle. And I'm going to call that W sub I. So it's a lowercase w. It's not capital W. So it's not work. But this W stands for width. And the I represents one of a million different slices I could draw in my triangle. So it's just like the I stands for a random slice. Okay, so it's the width of a random slice in my triangle. So from there, let's think about the force on just this slice. Okay, so the force on just this yellow slice that I have. So the force on this slice, okay, we can describe it as being density times gravity times the depth of that slice, because remember the slices at the top have less force than the slices at the bottom, and then times the area of the slice, okay? So let's see what this gives us. Our density is going to be our friend rho. Okay, now the density will be different for different fluids that we look at. So water has a specific density, oil has a different density, and if there is a density, that will be listed in the problem for us, okay? Now, in terms of the gravity, we'll just leave that as a g for right now because we know that's a constant based off of whatever it is that we are looking at. That gravity on our planet is constant, right? Now, the depth of this slice. What is the smallest value that the depth could be?
3.
3. How did you get 3?
You said that or technically the bottom of the plate or top of the plate, whatever you want to call it, it starts at 3 meters.
Yeah, so if I was looking at the very top slice here, that would have a depth of 3. What is a possible depth for the yellow slice that I have in the diagram?
4 minus y.
Give me a number. Like, what could that depth be?
4.
It could be 4. Okay, how did you get that?
Well, it's got to be between 3 and 7, and it looks closer to 3.
Okay, so it's between 3 and 7, right? 3 for the reason that James said that the top slice is at 3, and then 7 because we only go down 4 meters, another 4 meters. So it can't be more than that. Now, this depth part we'll talk more about on Monday, but there's a lot of different ways that you can set up your XY coordinate so that you get a specific depth equation, okay? So for right now, let's say that our depth for any random slice is going to be the minimum it could be, which is 3, plus whatever the y value is of that given slice. Okay. So that equation we'll play around with. There's a few different ways to set it up, and we'll talk more about that on Monday. Okay. Now for the area, how can I represent the area of the yellow slice with however I labeled it above?
W sub I times dy.
W sub I times dy. Yeah, exactly, right? Because it's a rectangle, so length times width gives you the width times the height, which is dy, okay? All right, so let's keep going. We've got rho, we've got our density, we've got our gravity, we've got an expression for our depth of the given slice. And now we want to think about a way that we can write the width. However, because I have a dy, I would like that width equation to be with y's, right? Because all my letters need to match, because eventually I'm going to take not just this one slice, but all of the slices. And so I'm going to be integrating so I can add them all up. So here's how we find the width equation for this particular shape. Now the width part is going to change for every type of shape that we see. So we're going to highlight a few of the sort of like predominant cases here, and then we'll think about you know, how it's different for each one, okay? But I'm going to take my triangle and I'm going to redraw it here with maybe some of the labels that we've seen. Okay. So I know that at the top of this triangle, it is 5 meters. And I know that the whole triangle has a height of 4 meters. But let's go back to the idea of similar triangles. And let's say I just wanted to find the ratio between this height, or the base, and the height, okay? I know that 4 over 5 is the ratio between the height and the base of the triangle, right? So 4 over 5 is just the ratio of the height to the base. What is this purple piece? Like, what have we labeled this previously?
Midpoint.
I don't think we've talked about midpoints today.
You labeled it a similar triangle?
Similar triangle. But what does that horizontal line represent in like some of the other diagrams we've seen?
Like 4 minus y.
5 minus x, 4 minus y. It could be 5 minus x, but we could even also just think about this as the width of a rectangle, right? That's okay. It's Thursday. It's the end of a long class. So what I could equate 5 with is w sub I. Like 5 is the maximum width, but for any width of a given slice, it's going to be the width of the slice. Now, I love where we were headed with some of that, like 5 minus x or whatever, because if we say that this distance is y sub I, or the y value of a given slice, how big is this distance?
4 minus y sub I.
4 minus y sub I, right? And so 4 minus y sub I is the height of the similar triangle. So that's going to go here, 4 minus y sub I. Now, if we want to have our w sub I, that means we need to take this equation. We need to isolate w sub I so that we can substitute it into our formula. So if we do a little bit of algebra, we will get that w sub I equals 5 times 4 minus y sub I over 4. And so that is what I can put in for my w sub I. Okay, so all of this, like this whole equation that we have right now, all of this is to say that that is how we find one slice. And because there are an infinite number of slices, and I'm not trying to sit here and find every single slice and then add it up together, what we're going to do is instead say, hey, let's use integrals, because an integral adds up a whole bunch of different things as long as they follow the same pattern. And so in this case, that pattern they're following is the shape of the triangle. So we're going to take our equation, rho times g times 3 plus y sub I times 5 times 4 minus y sub I over 4 dy. And we're just going to get rid of the i's. Okay, we get rid of the i's because now the I is taken care of by your bounds in the integral. So we can pick all of the y sub i's between whatever our bounds are. So force on the whole plate can be represented by this. The integral of rho times g times 3 plus y times 5, 4 minus y over 4 dy. Now, what are our thoughts for the bounds? Where are we going to start counting? Where are we going to stop counting?
3.
Say we're going to start at 3. Any other guesses?
0 to 4.
0 to 4. Okay. So that's a really good thing to bring up, because the bounds that we have could be different depending on how we set up our integral. Because I originally said 3 plus yi, what I was saying is that I'm almost taking this and this as my coordinate axes. So I have to include the 3 because that's above my axis. And then I have to include the y sub I because I have a distance underneath there, okay? And so in this case, we're actually saying like 3 minus y sub I, but that minus minus turns it into a plus because like all those y values underneath are negative, all right? But we've taken care of it with our 3 plus y. So because we're starting at the top of the plate, we're going to consider that kind of like if we start with the natural length of the spring, we start at 0. And then we're sort of counting all the way to the biggest height of the plate, which is at 4. Okay. So now that we have this whole equation, let's see what we actually need to integrate, because some of these are constants, and so we can pull those out to the front. Okay. So let's shrink some things. Okay. So as we are integrating, all right, the 5/4 can come out to the front, the rho can come out to the front, the g can come out to the front. Then I'm left with the integral from 0 to 4 of 3 plus y times 4 minus y. Okay, so as gross as that intermediate step looked, once we pull out all the constants, it's actually just foiling, power rule, and that's it. Okay. So let's see what we get. 5/4 rho times g, the integral from 0 to 4 of 12 plus y minus y squared dy. And then we integrate. And we get 12y plus y squared over 2 minus y cubed over 3. And we're going to plug in 4, and we're going to plug in 0. Okay, now this is nice because I don't have to plug in the 0 because that'll zero out everything. And so we end up with 5/4 rho times gravity. And then we are, once we combine everything on the inside, when we plugged in 4, we'll get 104 over 3. Okay. Now, if we wanted to get a numerical answer for this, then we need to really consider the units that we're working in. So since everything is given in meters, okay, we at the end want to make sure that we have the right density and the right gravity for the meters. And so when you're in a case with meters and water, the density of water is 1,000 kilograms per meter cubed. And gravity in these units is 9.8 meters per second squared. So at the end, what this is going to give us is going to be in newtons. All right, and so we can plug 1,000 in for the rho, we can plug 9.8 in for the gravity, and then we'll get a final numerical answer for this problem. All right, so let's just calculate that out, see what we get. So 5/4 times 1,000 times 9.8 times 104, and then divided by 3 should give us a lot of force on this plate that's been submerged under the water. Okay. Now, I think this is a good stopping place for today. When we come back on Monday, we'll work through the other examples and get just more familiarity with the setup, because I think it's really hard with the depth in the area. That's probably the hardest part of setting things up, is like, how do you know what formulas to do? And a lot of it is you just got to be really comfortable with coordinate systems and similar triangles or whatever shapes come up, and writing those formulas. So I want to focus on those skills on Monday. Okay. So I'm going to stop the video here.